Okay.
Okay, let's start.
Okay, start again. Okay, again, welcome to everybody. This is session 2, is integrating renewables in the energy market. We have 3 speakers that I see here. So welcome to all of you. And the integration of renewable in a competitive electricity market is a hot topic for regulators and also for researchers. And the researchers tried to find the optimal scheme that accommodates many issues. So on the one hand, we would like to promote competition to lower electricity prices, but we also would like to incentivize investment, especially in the new technology. So we need regulation to support decarbonization. And finally, we have to deal with technical constraints, both in production and in transmission distribution. And I believe that most of these topics are considered in the papers presented in this session. So I don't want to lose the time. I will present the speakers before each presentation. And just few warning for speakers. You are 3, so I think you have 20 minutes for your presentation. Then we have a Q&A time, and attendees, if any, are requested to write the questions in the chat, and I will deliver the questions to speakers. Please try to be strict with the time allowed, because someone has told me that they simply will close the Zoom session when the time elapses. So please be strict. So the first speaker is Marina Bertolini, and she is a postdoc research fellow at the University of Padua, and she's going to present a paper that contains a simulation exercise comparing costs associated with different market models for balancing energy supplied by variable and distributed renewable energy sources. So Marina, the floor is yours. Please do your presentation.
Okay, thank you. Thank you all for being here, and thank you for the presentation. Now I share my screen so I can show you something about our work. Okay, this is a work I did with Marco Agostini and Massimiliano Coppo from the Department of Industrial Engineering here at the University of Padova, and with Fulvio Fontini, who is my supervisor at the Department of Economics and Management in the University of Padova. The title of the work is The Participation of Small-Scale Variable Distributed Renewable Energy Sources to the Balancing Services Market. Long title, and it contains all the key elements of this study. So as you all know, the recent development of a number of small production plants made grid management challenging, as we need to integrate all the distributed energy sources which are scattered in the territory. And these can increase costs, for example, for reserve margin provision, as you, especially for non-dispatchable energy sources, you need to have a reserve to cope with sudden lack of energies. And also there is the risk of islanding in case you have technical failures due to overload. The Clean Energy for All European package still foster for the investment in renewable energy. So it is clear that we need to find a way to integrate also new small agents in the market. And designing new markets is a major issue for the functioning of the whole energy system. New agents, when we speak about new agents, we speak about prosumers, of course, but also small power plants, and now also of aggregators. Aggregators are a reality now in some European countries, for example, in Germany. Not so much regulation dedicated to aggregators by now. And also the market functioning will be highly affected by these new agents. Also, existing agents shall be reconsidered and re-regulated, and in particular DSOs, distribution system operators, are the core, the central point in the new regulation, as they have a key position in the distribution, in the network, as they manage the distribution, and also they are unbundled now, of course, with other activities, but maybe with the other activities we need to call them back in some part of the market. So, and this is still an open point, highly discussed in the literature. So it is necessary to study possible ways in which variable distributed energy sources can participate to the new markets, also taking into account technical issues together with economic issues. And this is our first interdisciplinary attempt. So we approach the design of new electricity markets together with our colleagues from the Industrial Engineering Department, considering both economic and technical implication of the two alternatives we are studying here. We will investigate the impacts of the two different market designs on the social cost of the balancing service. So we provide a model for calculating the overall social cost of balancing services, and try to define which is the cost in the two different scenarios. So this is our framework. In the paper, we analyze the functioning of balancing market, as I told you. In the first regime, we call them commercial aggregation. There offers are aggregated by one or more aggregators to provide balancing services without considering technical feasibility of the offers. And this is quite similar to what is happening also now for those who can act in the balancing services, in the balancing market, sorry. And the second model is a technical aggregation model. And under this framework, the DSO is responsible for keeping an agreed exchange path with the TSO, being responsible for local balancing and choosing resources to be called to the market. So also considering the structure of its network. These two models are two polar models, and they come from the literature. There have been some simulations, some technical simulations for the two cases. We chose these two cases because they are one opposite to the other. Of course, in between we have many many degrees of responsibility for the DSO at local level. The target of our regulation is to choose the market that minimizes the overall cost of balancing. So, and this balancing process has three main actors: the TSO, the transmission system operators, who is managing the whole system and need to keep the system balanced. The DSO, who is managing the distribution network, and the aggregator or aggregators that offers balancing services on the exploiting their availability. So we have, in the model, we have by now only one aggregator. In the appendix, we also show the same exercise with many aggregators, and this does not add much to the discussion. So to keep it simple, we will speak about only one aggregator, and we will see that in the second model, these can be also overlapped to the distribution system operator. The model only considers the distribution network, so there are no interplays between distribution networks. And also among agents in the distribution, since they are small and they cannot affect the market. To sum up, the model one, the commercial, in the model one, the aggregators collect their offers and present a single offer for upward energy, and another one for downward energy. As you know, balancing has two directions. Sometimes we need to have more energy, so we need to have upward offers, and sometimes we have too much energy in the network and we need to cut some productions, and these are downward energies offers. Then the TSO select the offer and submits the dispatching order to the DSO for the technical feasibility check. So here the information comes from the distribution networks, arrives to the DSO, and then the DSO only acts for a check. The DSO can decide to disconnect the well, let's say to refuse the all offers in case of risks or non-technical feasibility. And then the TSO buys residual demand from high voltage flexible resources connected directly to the transmission network. In the second model, the aggregators collects the availabilities for upward and downward services, but in this case, it specifies the composition of the offers to the DSO, and the DSO, who knows the network, can calculate the optimal power flows, also considering its constraints. And the DSOs has the target of compensating deviations from an agreed pattern, which is a duty for the DSOs to be keep at the contact point with the transmission network. Then again, the TSOs buys residual demand from the transmission networks to compensate the balancing in case that the distribution network is not sufficient to cope with the balancing need. So this is the process. I already told you most of this, but we can see that there is the balancing need, which is the difference between the expected energy exchange and the realized energy exchange. We have the offers for upward, which is identified with the plus, and the downward offers, which are the minus. And then in case of risk, the DSO can disconnect all the DDRs. And in this case, you have curtailment costs because you have more balancing needs. So if the DSO is forced to cut all the local production, of course, you add more need for balancing because you don't have all the productions from renewables at the local level. And then the TSO needs to buy more from the high voltage resources. The overall cost of balancing is represented by this equation. So the total cost is the price for balancing P star plus and minus are the prices for balancing from high voltage resources multiplied by the expected energy need bought by the transmission grid, plus the price paid at local level for balancing. So PA plus and PA minus are the prices respectively from upward and downward services provided at local level here and here, plus PZ. That can be seen as a consequence of a wrongly incentivized bidder, as it represents technical constraints that do not allow for the use of distributed energy sources when needed. We will come back later on this. We test our model in a network which is defined in literature, so you can read in the description and in our paper, which is a working paper of the Marco Fanno, which is our department. But this is a test, a network test we use for some simulations. And this is its structure. So we have residential feeders, commercial feeders, and industrial feeders here, and some VDER connections, which are, there are a lot of connections here, and they are mainly photovoltaic and wind. We use the two assumptions for residential, commercial, and industrial loads. We use these patterns in table A. And here you can see the typical consumption pattern for different type of consumption. So, for example, the residential one is higher in the evening. Industrial is always present, but there is more consumption in the central part of the day, and so on. And then here we have productions at local level with the typical PV production with the unproductive period till 6 a.m. and then from more or less 8 p.m. in the evening. And then wind, which is unpredictable but always present alongside the 24 hours. We made some simulations with parameters which are, for example, a 20% of the deviation for generating profiles and other shocks that after an iterative process gave this scheduled profile and the perturbated profile. So we have the blue line that represents what we expect and at time 0, and then the orange line, the red line, that shows what actually happened in different times. And then we have the exchange. So as you can see here, you have both upward and downwards shocks. So here you have the request in blue for balancing services and the offers at local level, upward and downward. What I forgot to say you that we assume that photovoltaics will reserve a part of the production to offer upward services. So they don't sell all the production to the standard market, but they keep 10% of production to play in this balancing market. And then they can offer to go to zero, so completely disconnect in case of downward service needed. For the wind is the same. So there is a quote in regarding the upward offer. There is a quota which is fixed by now, as they can't play in interactive game. So they have a 10% of their production which is reserved to play in this specific market, and that's why a photovoltaic can decide to produce more. Otherwise, if they sell all in the normal market, they will not have sufficient capacity to cope with the offer. And also, please note that we are not considering the presence of batteries by now. This simply will make both photovoltaic and wind more predictable and let's say enable the agents more to play more on the markets. This is an extension that makes the system work better.
Marina, you have 2 minutes to conclude.
Okay, so I go quite fast now. I'm sorry for the length. So here we have the accepted offers and the residual balance that need to be bought in the high voltage services. And here we can see the curtailment. These 3 peaks represents the point where the network fails and you cannot use your renewables because the network is not supporting the services. So here I will need to skip these. These are the energy flows in the different cases. Please note that we made some simulations with the derating. As I told you, we were initially assuming a 10% of the rating to participate to other markets, but my colleagues also did some simulations from 5 to 20%. And then here we also change the generation mix from 100% photovoltaics to 100% wind with many differences here in the model 1 and model 2. Oh, so differences among the 2 models. Downward service increasing the rating percentage lead to higher need for balancing in all scenarios. Higher the rating, lower the probability of congestion, and upward services are highly dependent on generation mix and ratings, also because photovoltaics are correlated and wind here are not correlated. In market model 2, what is relevant is that Z is always equal to 0 because the DSO is forced, incentivized to use its resources at the local level. The DER can decrease the entire production in case of 100% of photovoltaic. Of course, this is not true during the interval in which photovoltaic is not producing. As we remove the indivisibility constraint of offers, we can use more offer from the local network because the DSO can decide to use only feasible offers, while in the first model, which is a commercial one, you need to take all the offer if you want to balance from the distribution. Okay, these are the costs. We had some assumptions about costs and about prices, and these are the costs we reach in different models with different shares and of the photovoltaic and wind, and with different rating. as you can see, model 1 is not always worse than model 2 and vice versa. Conclusions: a lot of curtailments in model 1 represent the missing integration of VDER in the system, and this is one of the most important points we want to focus on, because if you neglect to consider technical constraints, you will force the network to pay more for these local productions. Model 1 leaves DSOs outside the balancing market. Model 2, on the contrary, asks them to be responsible for the integration of renewable at the local level. And I think that this is an interesting point also for future developments. Model 2, as I told you, is not always preferred because, of course, these local resources sometimes are more costly than the high voltage resources. So we have a trade-off between promoting renewables at local level and pay more for energy. Overall, commercial aggregation is preferable when the penalty price of curtailment is not low, and this is a policy parameter. And technical aggregation is preferable if the share of wind is higher, lower level of the rating capacity, or with high explicit penalties for curtailments. And again, these penalties are something we have to decide at policy level. Thank you for your attention. You can read the paper here in our page, and I'm open to questions later on. Thank you.
Okay. Thank you, Marina, for your very interesting presentation. I don't see questions in the panel here. Okay, Angelo has got a question.
I have a couple of questions regarding the model of the network and the market model.
Mm-hmm.
Regarding the model of the network, you used IEEE 33 bus, and you distributed some renewable sources. Photovoltaic wind, you also consider the possibility to include other kind of generators with more constant profile, by example, biomass generator or mini hydro generators.
Yeah, of course, this is possible. We decided to keep the example extreme. So we decided to include the, let's say, the most unpredictable sources, and also not to consider the possibility to store. They both, so storage and also other production plants from renewables, which are more stable, for example, biomass, are, of course, it is possible, of course, to include them in the model, and you will have better results because they are less costly, at least in some cases. More predictable, and will keep the local market more stable. The idea of this first simulation was to keep the model extreme. So we want to stress a lot of the balancing market. But of course you can include them.
Okay, I have a question, but I think I will write the question in the chat, because we run out of time, so I'm forced to introduce the next speaker. So thank you, Marina.
Thank you for
now I introduce Matthias Ondra, who is assistant professor from Vienna University of Technology. And he's going to present a paper which is about the optimal investment choice in renewable, made by manager who faces a typical market scenario in which the output is stochastic, prices are variable, and the scenario is that she can buys energy in the market at a variable price, but if they sell energy, they face a feed-in tariffs. So variable price for buying and fixed price for selling, if I have well understood. So Matthias, I leave the floor to you for your presentation.
Yeah, thank you very much. So can you see my presentation? Yes, okay. So my name is Matthias Onwer. I'm from the Vienna University of Technology, and today I'm going to present a joint work with Thomas Dangle with the title Feed-in Tariffs and Renewable Energy Investment Under Uncertain Production Volumes. So let me first of all give a short overview of the presentation. In this paper, we analyzed the energy manager's investment decision in renewable energy technologies from the prosumer's point of view. So this means that we consider the problem of an energy manager who aims at investing in an energy park consisting of renewable energy technologies. And this energy park is primarily designed for own consumption to cover the firm's demand by minimizing the costs of power procurement. So we assume that the energy park is connected to some local grid, such that in case of a shortfall in the power supply, energy that is needed to cover the demand can be purchased at the energy price, and surplus power that is not needed to cover the demand, so excess power, can be sold to the grid, for example, at the level of the feed-in tariff. So concerning the remuneration policy of the feed-in tariff, we consider a market-independent fixed policy. So that means that surplus power can be sold at a fixed price. So the total costs of the energy park therefore consist of investment costs, which are considered as sunk costs, then the expected costs of a power shortfall, and expected revenues of selling surplus power to the grid. The problem associated with investment in renewable energy technologies is, of course, that the production volumes are uncertain. So therefore, investment in renewable energy technologies introduces uncertainty and therefore also risk in the energy manager's investment decision. So therefore, the research question addressed in this paper is, how does the optimal level of the optimal level of investment, and therefore also the optimal probability of demand coverage via the self-generation facilities, change with the price of the balancing energy, as well as with the level of the feed-in tariff when the production volumes are uncertain. So in the first place, we therefore analyzed the energy manager's optimal investment decision, where the firm is considered to be a price taker. However, the question of how firms optimally react to policy changes in the level of the feed-in tariff is of course also important from a regulator's point of view to evaluate, for example, the efficiency of the feed-in tariff mechanism. So one important question from the regulator's point of view is of course which level of the feed-in tariff incentivizes the energy manager to some certain investment decision. So to begin with, I will talk about the handling of uncertain production volumes associated with renewable energy technologies, since this is the most important aspect in the model. And the primitive of this approach is that renewable energy output is uncertain, and that each technology which is included in the renewable energy portfolio exhibits a specific exposure to risk, which is a risk to power shortfall. So in the figure, the power output for 1 unit of installed capacity is plotted for the two most used renewable energy technologies, which are wind power in the upper figure and solar power in the lower figure. So in the upper figure for wind power, we observed that especially wind power exhibits the characteristics of a heavy-tailed distribution. And this is due to the threshold cut-in and rated output wind speed, below and above of which the power output is 0. So since each technology is associated with this kind of specific distribution, power output distribution, the energy manager can look for a diversified portfolio, which is a mix in the generation technologies in order to reduce the exposure to risk. So in this histogram, an energy portfolio consisting of 1 megawatt of wind power installed and 1 megawatt of solar power installed is illustrated to show the effect of risk shaping by choosing a diversified technology mix. So therefore, by choosing an optimal renewable energy portfolio, which is optimally choosing the installed capacities, the energy manager is able to avoid specific risks, for example, tail risks introduced by wind technology. So with the underlying primitive that the energy manager can shape the risk distribution by choosing the renewable energy portfolio, the question arises, of course, what the optimal technology portfolio is. So therefore, we consider a prosumer who minimizes the total costs of power procurement. The underlying constraint is, of course, that the firm's electricity demand can be covered, either by self-generation facilities or by making use of an outside option and purchase external power. So given a renewable energy portfolio denoted by a small x, where the components of this portfolio represent the capacities installed in a certain technology, the associated difference of demand and supply is denoted by this capital X, and of course depends on the chosen portfolio. Based on the choice of the renewable energy portfolio, both the shortfall power and the surplus power can be expressed in terms of the maximum function of this difference of demand and supply. Moreover, weighting the shortfall power and the surplus power with the respected prices, which is of course the shortfall power with the energy price and the surplus power with the level of the feed-in tariff, gives the capitalized losses or gains associated with the renewable energy portfolio over the expected useful lifetime of the energy park, denoted by delta T. So in order to evaluate the energy manager's costs from a risk management perspective, we denote the probability of demand coverage via self-generation facilities by chi. And consequently, the probability of a power shortfall is given by 1 minus chi. So therefore, this level of reliability, chi, also relates to the level of energy autarky and can be interpreted as the probability that the energy park alone, so to say in a standalone application, is able to cover the firm's demand. So by applying the total law of probabilities, the cases of a shortfall power and surplus power can be distinguished, and we observe that the expected capitalized losses or gains are given by the conditional value at risk metric. So in total, the prosumer aims at minimizing the total costs, which consist of the investment costs and the capitalized losses or gains, subject to a budget constraint which limits the initial investment. So, and based on this optimization problem under uncertainty, we determine the optimal level of investment in renewable energy technologies from the energy manager's perspective and analyze the effect of different energy prices and different levels of the feed-in tariff, which are denoted here by the Xi minus and Xi plus, and illustrate the effect of the different prices on the optimal portfolio selection. So we evaluate this model in a use case where we consider an energy manager who aims at minimizing these total costs such that the hourly demand can be covered and the budget constraint is specified to 1 million euros. So we consider only 2 renewable energy technologies in the use case, which are wind and solar power. And note that in this use case, we only consider a daytime model where the opportunity to invest in solar technology is valuable, since in the nighttime, no solar power is available. So the prices of the investment goods are specified in terms of the costs per installed capacity of wind and solar technology. and are given by 1,400 euros per installed capacity of wind and 1,000 euro per installed capacity of solar power. And the range of the energy price and the level of the feed-in tariff that we consider ranges from 0 to 100 euro per megawatt hour. We use a data-driven optimization approach to solve the optimization problem. This means that we sample from real-world output data of the wind speed and solar irradiance for the town of Schwechat, which is a town near Vienna Airport, representing a typical location in Central Europe. So wind speed and solar irradiance are translated into power output of wind power and solar power via the physical energy model given by these characteristic power curves illustrated in these figures. So let us now analyze the computational results from this use case. The first thing we note is that the investment behavior of the energy manager can be characterized in different regions depending on the level of the feed-in tariff, which is on this x-axis here, and the energy price on the y-axis. First, we characterize the investment decision based on the criterion if the energy manager observes losses or profits in the total evaluation of the energy park, which means investment costs and the capitalized losses or gains. So the loss region is denoted in red and the profit region is illustrated in green here. And note that the boundary of the two regions illustrates the break-even line associated with the optimal portfolio selection. So even if in case if the energy manager observes losses, the total costs can of course also be decreased for investment in renewable energy technologies compared to the benchmark scenario of purchasing totally outside power. So also in case the total project refers to losses, investment in renewable energy portfolios can of course decrease the total costs. So we also observe that there is a threshold level of the feed-in tariff, such that even in case of a vanishing energy price, which means that energy comes for free, profits can be created, which is indicated by this point here. So now let us discuss the investment behavior with respect to the probability of demand coverage. So the probability of demand coverage is the probability that the energy park alone can supply the demand and is therefore related to the level of energy autarky. So in the investment model, the probability of demand coverage is an endogenous parameter which depends on the external costs, which are the energy price and the level of the feed-in tariff. We can classify the investment behavior into different regions depending on the energy price and the level of the feed-in tariff. So in the region R2, which is characterized by low energy prices and low to medium levels of the feed-in tariff, the optimal decision is to refuse to invest in capital-intensive renewable energy technologies, since the opportunity costs of purchasing power at price Xi minus in this region here are lower. So therefore, when no investment is made in renewable energy technologies, the optimal probability of demand coverage in this region is of course also zero. So next we consider the case of a vanishing feed-in tariff illustrated by this line here. And we observe that even without a feed-in tariff, so a feed-in tariff of zero, at some threshold energy price, investment in renewable energy technologies becomes a valuable option, which defines this investment region R1 here, where the energy manager invests in renewable energy technologies. In this region, investment in renewable energy sources becomes a valuable option. This is due to the fact that, or so to say, this is due to the fact that the feed-in tariff in this region works properly. This means that for a given energy price in this region, the optimal decision of the portfolio is such that the probability of demand coverage via renewable energy sources is increased gradually, as can be observed when moving along this line here, that the probability of demand coverage increases. So next, the profit region R3 here is characterized by high levels of the investment, where the budget constraint can be exhausted. So, however, the optimal portfolio selection also in this region might differ considerably, depending on the level of the feed-in tariff and the energy price. As it is indicated in this line here, we observe that in this region, R3, overcompensation might occur. So in this case, the energy manager decreases the optimal probability of demand coverage, which with increasing level of the feed-in tariff. So we can observe that moving along higher feed-in tariffs, suddenly the probability of demand coverage is decreased again, although the feed-in tariff increases. So let us now investigate the cost reduction potential of the feed-in tariff mechanism when it works properly, so in the region R1 and R2. So since the feed-in tariff works properly there, this means that no overcompensation occurs. We observe that the total costs can be decreased. So the dashed line here denotes the benchmark scenario of no investment in renewable energy technologies, which means the total power to cover the demand is purchased, for example, via pre-contracted energy. So we already observed there exists this threshold energy price denoted by Xi prime, where investment in renewable energy technologies is valuable. So we observe that above this threshold price, the total costs can be decreased compared to the benchmark scenario by investing in renewable energy technologies. So indeed, we observe that the feed-in tariff is effective in this region because it reduces the total costs with increasing feed-in tariff. So in order to evaluate this cost reduction potential more thoroughly, consider the figure on the left-hand side, where the cost reduction potential as a function of the energy price for different levels of the feed-in tariff is plotted. So with cost reduction potential, the relative cost decrease compared to the benchmark scenario of a vanishing feed-in tariff is meant. So we observe that for a fixed level of the feed-in tariff, the relative cost reduction potential is increasing in a concave way with increasing energy price. So similar on the right-hand figure, the relative cost reduction potential for a fixed energy price as a function of the level of the feed-in tariff is illustrated. And again, we observe that the cost reduction potential is increasing, but this time in a convex way, with increasing levels of the feed-in tariff, indicating the effectiveness of the feed-in tariff remuneration scheme. So overall, however, we observe a non-linear effect of this cost reduction potential with the feed-in tariff. To sum up, we analyzed the energy manager's investment decision from a prosumer's point of view in renewable energy technologies in the presence of uncertain production volumes and a remuneration policy of a fixed and market-independent feed-in tariff. We show that the underlying optimization problem can be reformulated in terms of the conditional value at risk and demonstrate the model in a use case where the energy manager has the opportunity to invest in either both wind and solar technology. So the optimization problem is solved by a data-driven optimization approach, which uses real-world output data. So we identified the regions depending on the level of the feed-in tariff and the energy price, where the energy manager refuses investment in renewable energy technologies, and the region where the remuneration scheme works properly. And this means that the energy manager increases the probability of supply of demand coverage with increasing levels of the feed-in tariff. So then we also discussed the presence of overcompensation, where the energy manager's optimal decision is to decrease the probability to cover their own demand via self-generation facilities, and therefore invests in inefficient renewable energy portfolios that promote overcompensation. So thank you for your attention, and now I'm open for questions.
Thank you, Matthias, for your very nice presentation. And there is a question from Fulvio Frontini, who is asking about the behavior of investors in region 3. If the energy price is high and investment costs are constant, why should a rational investor reduce the investment in renewable if the feed-in tariff rises? This is the question.
Okay, so the answer to this question is due to the fact of overcompensation. So if we consider again the formulation of the optimization problem here, we observe that two parameters are included, the energy price and the level of the feed-in tariff. And now consider a situation where the level of the feed-in tariff is much higher than, or is higher than the energy price. So therefore, one term in this objective has a higher impact. So this means that the optimal renewable energy choice, according to this objective, also changes, and it's now better to choose portfolios that promote overcompensation, so surplus power that can be sold at the level of the feed-in tariff, because the feed-in tariff is exceptionally high. So a cost minimizing or profit maximizing investor will choose a portfolio in this region that refers to overproduction. But this also has the effect that the probability of demand coverage is not as high as it could be, but the main focus is to look for overcapacities. And therefore, we observe overcompensation here because it simply refers to higher profits.
Okay, thank you, Matthias. I have one more question. It's about the way you model energy price. Of course, you make a stochastic optimization, but we should notice that when the investment in renewable increases, usually energy prices decrease. So there is an impact of more production, renewable production in the energy market. Did you consider this issue, or simply you simulate, you use various energy prices as they could be emerging exogenous way in the market?
Okay, so the main focus here, so thanks for this question. The main focus here was to analyze the effect of uncertain production volumes. So we just focused on the uncertainty on the production side, and therefore we considered at this point only deterministic prices. Okay. However, we could also integrate, since this is a data-driven approach, a stochastic energy price, for example, which is correlated with the power output for renewable energy technologies. So that means, yeah, exactly. So we can implement in this way what you mentioned, that with increasing investment, that the energy price is decreasing, for example, and via these correlations, we could implement this effect and observe and analyze this on the optimal investment decision. Yeah, thank you for this point.
Okay. Are there any other questions? No? So thank you very much, Matthias. We are going to the last paper of this session, which is presented by Angelo Facchini, who is assistant professor in the School for Advanced Studies at Lucca. And he's going to present a paper that develops a tool for optimal spatial installation of renewable, considering both wind and photovoltaic. So, Angelo, please, the floor is yours. Angelo, I can't hear you. Please activate the mic.
Can you hear me?
Okay, okay, now it's okay.
Okay. So, we are also dealing with a portfolio approach to energy sources planning, and we are considering regional level. Come si fa avanti? Okay. So just a bit of a scenario, as we know, renewable energy sources are one of the key strategies to decarbonize the electricity sector in the next coming years. Basically, there are two ways to deal with the problem and the issue of fluctuations. Are just to use energy storage in order to not challenge the stability of the electric system, but another possibility is to program renewables and to deploy renewables in a way that reduce fluctuations from their intermittency. In a paper that we published 1 year ago, about 1 year ago, we used the portfolio theory, Markowitz portfolio theory, to define an optimal criteria for the spatial installation of renewable sources, mainly coming from wind and photovoltaic. This because we focused on anti-correlated Gaussian sources. We now go further, so because this theory, this paper was based only on stochastic analysis, and we go further by developing a case study in Tuscany with two strategies. The first strategy is to consider the current capacity in a certain region and to expand some one or more station in this portfolio, in this generation portfolio, or to invest in new installations. So the idea is to invest in both strategies by considering an optimality condition that considers and that for which the objective is to not increase or to increase to minimize the fluctuations that new renewable plants or the addition of new generation capacity do not minimize the influence of fluctuations while maximizing the average production over the time span of 1 year. So what we are basically doing is to start from the theoretical approach, from which in this paper we consider a set of Gaussian sources. We demonstrated that the use of anti-correlated sources leads to we mathematically define a frontier of an optimal frontiers for feasible portfolios, and with some analytical data and some experimental data, we showed that the optimal boundary can be pushed up by increasing in the portfolio the presence of anti-correlated sources. Now we move from this theoretical approach, and we considered a case study in Tuscany based on there is an histogram that is in a bad position. Okay, but we considered a case study in Tuscany starting from the actual data of two types. The first type of data is the data from the meteorological stations of solar irradiance and wind speed and wind energy. So we acquired the data for the all weather stations in Tuscany for a time span of 1 year. And we also get data from the actual position and size of the wind and photovoltaic generation plants in Tuscany with a threshold of 200 kilowatts, as far as I remember. So the idea is to analyze the correlation of all the weather stations and all the power stations present in Tuscany in order to understand, in order to show how and if the wind and the solar sources are correlated. So the first step is to study the correlation of all these sources. And the second step is to considering accurate models of photovoltaic panels and wind turbines. We generated we projected a generation profile according to the data of the weather stations. So the first step is the correlation analysis of all the stations that we are able to filter out from missing data or from generators with non-suitable size. And in the left panel, you can see the result of the correlation analysis. So on the axis, you will find the type, the order number of the stations considered. And here you will find the solar stations from 0 to 28, from 18. And here you will find the wind power stations. As expected, solar with solar, so this triangle here, all the solar stations, all the time series related to photovoltaic productions show a high level of correlations. This is quite normal. While wind power also shows a weak but positive level of correlations. Since we are looking for negative levels of correlations, the optimal mix under this point of view is the mix that is made starting and mixing aeolic and photovoltaic stations. So this partially confirms what we found, that by the modeling approach of the paper before mentioned. Here you can also find the correlation profile of the whole generation portfolio. So what we find is that there are the majority of stations are negatively or very weakly correlated, while there is, of course, I'm speaking about the mix of aeolic and solar, while there is a small amount of PV and aeolic stations that are weakly positively correlated. So this suggested us to use some constraint and to make some further analysis regarding the correlation profile hourly, since we are interested in the yearly performance of the system, but we decided to also investigate which is the profile of the correlation during the daytime, in order to disentangle the contribution from wind from the contribution of solar, expecting a peak of correlation, or better, a shift of the histogram of correlation towards the positive values because of the increased photovoltaic generation. We observe a small shift, but not so significant, from 6 to 12, more or less, the peak is conserved, while from at 15, so in the best, in one of the optimal generation moment, we observe this shift from negative to positive correlations, while at 21 wind, it's this is just the correlation of wind. So what we did in order to analyze the two investments scenario is to we considered both for expansion strategy and greenfield strategy. We considered an approach based on picking up each single stations present in our generation portfolio. We discarded the actual values of the capacity of the power plant, and we decided to consider a standard generation capacity for both wind and solar stations. This because we were interested in showing and in isolate the only effect of fluctuations due to the intermittency of the sources. And so in the expansion strategy, we considered a number of runs for in which in each run we increase of 50% the nominal capacity of one existing station, both photovoltaic and wind. So we consider a portfolio, and in this portfolio we considered and we changed sequentially one single capacity of a station. This because we were interested to see and to understand how the correlation profile changes and how the generation profile of the whole portfolio changes by moving only one station. What we found is that, as expected, when increasing the generation profile, when increasing the photovoltaic power stations, what we obtained is in general a variation, a consistent variation of generation with respect to the original portfolio. But as a counterback, we also observed for all the photovoltaic station in which the investment was made, a consistent increase of the standard deviation, excluding this single station here. On the other side, if we consider the investment in increasing the capacity of wind power station, we find that the total increase of the production variation was much more limited, just because in Tuscany, the wind profile is very intermittent in several zones of Tuscany. So sometimes wind is not suitable for consistent power generation, while sun is much more regular. And we find that the large amount of more or less all the wind stations that were considered did contribute with a limited amount of standard deviation. So under the point of view of considering the stability of the portfolio, the wind generation should be considered, and we selected a best trade-off zone, that is this zone here, in which two wind stations and one solar station did perform better under the point of view of the trade-off between the increasing of generation while decreasing or while minimizing the fluctuations. The same holds for an greenfield strategy scenario, in which we considered to increase the portfolio of one single station picked up from another point, source point in Tuscany. And we also find that not all the positions are in Tuscany suitable for increasing the generation portfolio with one new unit, because of the different correlation values present in the different zones of Tuscany. But in general, we also find that there is one optimal boundary here, for which in some points generation, the delta of generation is in any case consistent, while the standard deviation is kept very low. From the point of view of power station based on photovoltaic, we did not find an optimal position for under the point of view of the optimality criteria defined above. In any case, you will find that in the greenfield strategy, just one single optimal station placed in an optimal position may generate and may generate a consistent amount of power. So by concluding, we considered a case study based on actual data on regional level. So we considered an optimal portfolio distributed on a wide region. So it's not a city, but is a region of Tuscany. We also made an attempt to provide some additional measures of efficiency that also considers the benefit of installing renewable sources and renewable energy sources in optimal positions that are considered by the point of view of the generation profile that one can expect from that station. The idea is to manage fluctuations since from the beginning, so ab initio management fluctuations by considering optimal positions. Then one can invest on batteries, on other means of mitigation, but first of all install the power plants where the effect on the global fluctuation is smaller with respect to other points. Of course, we are expecting, and we are doing computation about this. We are computing actually the boundary of the feasible portfolios, and we are expecting that this is a suboptimal position. It's a suboptimal solution for that. But in any case, we think that this may be a cheaper option than relying on ancillary market and spinning reserves. That is a usual approach in this kind of generation portfolio. So I thank you for the attention and for this presentation, and I also encourage you to submit in these two journals, Sustainability and Energy Sources, in which there is much attention is devoted to the topic of integrating energy and renewable energy sources in the territory. So I'm open to your questions, and thank you very much.
Thank you, Angelo, for your presentation, which has been really interesting. Are there questions from the floor?
Sorry.
Questions, perfetto.
Okay.
Allora, vediamo, non c'è. No questions as far as I suppose.
No, I don't see questions.
Okay.
Well, I have just one question for you, which is about the management, say the regulation of all your approach. So you are talking about the optimal geographical placement of renewables, and I believe this requires some sort of planning, some sort of regulation. While in Italy, at least in Italy or in the area that you consider, I think that this is mostly decided by managers and by some political and administrative constraint. So this is just a policy question. How do you think we can deal with this problem?
Oh yes, we have also we are still investigating which are the factors that allow the deployment of a specific renewable source on the territory. And what we find out is that usually a generation plant is deployed where the municipality or where the territorial policy bodies allow for the construction. So the idea is to suggest a further criteria that is not only based on the environmental constraint, by example, the valutazione di impatto ambientale, or the availability of power sources, or the proximity to secondary or primary substations, but to consider in the authorization or in the planning of future power plants also the suitability under the point of view of the impact of the generation profile of these power plants. It should be better, and we strongly recommend to consider the impact on the whole electricity system or the regional system of a single power plant under the point of view of the stability that the effects of the stability of this power plant. So it's better between two regions. It's better to choose the one that is that minimizes its impact. Even if considering a reduced generation. So in my view, the problem is not the generation, but is the effect of this generation on this on the regional generation profile.
So the final conclusion is that we need some central regulation.
Yes, no, the regulation is strongly needed.
Strongly needed. So decentralization of choices is not optimal in this context if you want to apply your method, your model.
Yes, it should be better to not completely decentralize, but to centralize some decisions about the feasibility parameters and the feasibility criteria of a power plant.
Well, I think this is generally a central issue in the regulation of electricity market. Too much decentralization, especially for renewable deployment, too much decentralization is not the best choice, probably. So we need some regulation.
Yes, I agree with you.
Are there some other questions? I don't see questions. So I think we can close this session. We are perfectly in time. I would like to thank you, all of you, for having been strict with the time in your presentation. And we had very interesting papers presented. And thank you very much for joining the session, for the presentation. And best wishes to everybody. Bye.
Thank you. Bye.
Thank you very much. Bye-bye.
Bye-bye.
Thank you.